The title of my talk is Velocity Distribution and Diffusion of an Athermal Inertial Run-and-Tumble Particle in a Shear Thinning Medium. So the audience here doesn't require any introduction to active matter, so I will directly go to the problem I have studied. The equation of motion of an active particle moving in a fluid is given by this equation. So here this eta is the thermal noise. So we are considering athermal particle. So by saying that, we are considering mass of the particle is sufficiently high so that we can neglect this thermal noise, and then we consider external force Fext to be 0, and Fact is the active force which we have modeled by an asymmetric dichotomous noise, and Gv is the damping force. So here for shear thinning medium, we modeled this damping force by a Coulomb tan hyperbolic function which look like this. Now here is the plot of this shear thinning function. So for small velocities, this behave like a linear friction. For high velocities, this behave like a solid or dry friction. So this is the equation of motion of a run and tumble particle in a shear thinning medium in one dimension. Here Xi is the active force. So we consider Xi to take values minus delta tilde and mu delta tilde. So mu is the parameter which characterizes the asymmetry of the active force, and this Xi transitions between these two states at a rate gamma. So here are the correlation average value of Xi and the correlation of Xi look like this. Next, we non-dimensionalize this equation of motion by rescaling time and velocity of this form. So our equation of motion reduces to this like this. Here Xi is the scaled active force, and the average value look like this, and the correlation becomes something like this. And here lambda is the scaled flipping rate of the active force. Now with this form of the active force, so the particle can take any values between Vb and Va. Okay, so this form suggests that our parameter delta will be less than 1, and also for any value of delta, so mu can take any value such that mu delta is less than 1. Next, we calculate the steady state velocity distribution function of this model using Fokker-Planck method. So I am not going into the details of the method. So eventually I ended up with this form of the steady state velocity distribution function. Okay. So here n is the normalization constant which I cannot obtain analytically because the integration of PSB doesn't have a closed form. For mu equal to 1, so that means the symmetric driving, symmetric active force, the form of PS is like this. And as expected, this PS is symmetric under the transformation B goes to minus B. So here is the plot of steady state velocity distribution function for delta equal to 0.6 and mu equal to 1.2. So when lambda is small, so PSB diverges at both the edges of the velocity domain. So if we increase lambda a little bit, we see that it diverges at one end and goes to 0 at the another end. As we increase lambda further, so it decays to 0 both the edge, but there is occurrence of two local maxima and a minima. As we go further, as we go increase lambda further, so these two maxima merges together near 0, and both the tail of the velocity distribution goes to 0. So in this choice of lambda, so one tail goes to 0 horizontally, whereas the another tail goes to 0 vertically. So if we increase lambda further, so both the tail goes to 0 horizontally, and these are the distribution function for higher values of lambda. And it is look like a Gaussian, and the peak of this Gaussian is shifted from 0 because our asymmetric parameter is other than 1. Okay. So here I tried to find the domain at which different transition occur. So near V equal to Vb, the PSB behaves like this. So at V equal to Vb, PSB approaches to infinity when lambda is less than 1 minus delta square, and PSB approaches to 0 when lambda is greater than 1 minus lambda square. Okay. Near V equal to Vb, I take the derivative of this, and it look like this. So the derivative diverges when lambda is 2 times 1 minus delta square. So basically what I can conclude is, like between lambda greater than 1 minus delta square and less than 2 times 1 minus delta square, PSB goes to 0 vertically. So that means that PSB has a cast-like singularity at Vb. So the behavior at V equal to VA can be obtained by putting delta equal to mu delta. Okay. And then we focus on the extrema of PSB. So that can be obtained from this equation, and we obtain this equation by setting the derivative of PSB to 0. Okay. And for mu equal to 1, the symmetric for any mu, so the solution will come from this solution of this equation. So which is very difficult. We tried with Mathematica and that didn't work. So for mu equal to 1, the solutions are u equal to 0 and u12 equal to plus minus tan hyperbolic inverse 1 minus square root 1 minus lambda. So two maxima occurs when lambda is less than 1 and greater than 1 minus delta square. So these are the two maxima, and u0 equal to 0 is the minima. So when lambda is greater than 1, these two maxima vanishes and u0 equal to 0 becomes the maxima of the velocity distribution. Okay. So for any mu other than 1, the two maxima appears when maximum of 1 minus delta square and 1 minus mu square delta square lambda is greater than this and less than approximately 1. So basically this condition guarantees this maximum value of these two guarantees that the tail of the velocity distribution goes to 0. Okay. So for any lambda, for any mu, when lambda is large, very large, so the maximum, so the only one maximum survives. So the position of the maximum is tan hyperbolic inverse mu minus 1 delta by 2. So mu equal to 1, again it becomes 0 as expected. Okay. So next we solve the equation of motion or the dynamical equations numerically. So first thing we test is the mean square velocity for different values of lambda and mu. So these data points are from the numerical simulation, and the solid lines are obtained by doing B square in the steady state regime using this semi-analytical approach. It's like we integrate these equations using the steady state velocity for using the form of the steady state velocity. So the lower part is just the normalization in. Okay. So in both cases we have good agreement with the semi-analytical data and the numerical data. Here are the some plot of velocity distribution functions for delta equal to 0.6, mu equal to 1.2 and different values of lambda. In all cases our velocity distribution function, numerical velocity distribution function matches with the theoretical normalized theoretical velocity distribution function in the steady state. Next we calculate the mean square displacement of the particle. So here we consider the mu equal to 1 case because pure diffusion arises when mu equal to 1. Otherwise our velocity distribution is shifted from 0. Okay, so there is some drift. So we avoid that by setting mu equal to 1. So we found that r square goes as t, so that implies that we have diffusive motion, and we obtained a quadrature expression for the effective diffusion constant using the method described in this paper. So here are the numerical data for effective diffusion constant dE. So that these data points are numerical data, and the solid lines are the solution of this equation for different values of lambda and delta. So here our numerical data is again in good agreement with analytical theory. Okay. So here is the conclusion. So the paper is currently at archive, and it got accepted in physics of fluid. Thank you for your attention.
Thank you. Questions? So you showed your calculation and results for velocity distribution. Do you also look at steady state position distribution?
So the particle can go anywhere. So the mean square displacement is running.
No, position distribution.
So we didn't use any confinement.
Sorry?
We didn't use any confinement. We didn't look at, I mean, because we do not have a confinement.
Okay, so it can escape to infinity in the long time limit. Okay.
So currently we are trying with confinement.
And for this mean square displacement, you every time start from the origin, or do you average over the initial positions as well?
We can start with any position, and then we have to subtract r minus r0 and then square. So that we can do. So even we can start with 0 velocity as well as non-zero velocity. So 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 it's like one class of active dynamics. So there is like Brownian dynamics. So what I'm saying is run-and-tumble means that it can go forward or it will, just stay and oscillate about the position. That is what is the tumbling motion. So it is between two states actually, minus delta tilde. So that is, so it tumbles between these two states. So it cannot continuously change. The force cannot continuously change. So it's just two. Yeah. So it is basically it mimics the bacterial run-and-tumble thing.
Can I ask?
Yeah.
So I guess the problem is motivated by swimming of bacteria in non-Newtonian fluids, right?
Yes. Yes.
Okay. So what is, so I can see that there is a transition which is happening, right, from superlinear to the diffusive
But
regime.
superlinear region will be
Correct.
always there.
Right.
Always
So-
there. So that is because.
So if I have to compare with respect to the realistic time scale, around what time it will happen?
Yes. So if you see, so this is 10 to the power 0 is 1. Now you have to compare with our time scale. Yeah, 1/. We have a time scale something defined like this.
Okay.
So we have a time scale defined like this.
All right. Okay. Thank you.
So inertia has some effect as well.
As there are no more questions, let us thank the speaker.